Do you know what is the pressure in Pascal that we are all under right now? 1 lakh Pascals. The air pressure in this room right now is very close to 10 power 5 Pascal, like 1 lakh Pascal. Compared to that, what?
His head is starting to ache.
Starting to ache. So if you have a container, imagine you have a container with gas at 20 Pascal inside. You know what pressure does, right? Pressure pushes on walls. So if I have let's say a tin can, it pushes, doesn't pull.
Yeah, it doesn't pull it. It's the outside pressure.
So there is from outside atmospheric pressure pushing in on it, which is 10 power 5 Pascal. And from the inside, if you have a gas that is pushing out with the, how much is it? 20 Pascal. What's going to happen to the can? It's going to get crushed. Really, it's going to get crushed. Okay. This is a problem. Actually, when you design submarines, right? Submarines are supposed to go deep into the ocean. Now, as you go deeper into the ocean, pressure increases. Now, within the submarine, the pressure is often 10 power 5 Pascal because submarines are supposed to house people. And we are used to 10 power 5 Pascal. But if you go deep into the ocean, the pressure outside would be, let me estimate. Do you again know the formula? Rho G H and all that?
Yes.
Rho G H?
Yeah.
Density of water is 1000. G is 10. Let's say you went, how much? 1 kilometer into the water. So again, another 1000 feet. Yeah? So how much is this? 10 power 7, right? 10 power 7 Pascal, right? So from the outside, there is 10 power 7 Pascal pushing in. You see, the submarine has to be designed in such a, you can't just take an ordinary car and put it, right, 1000 meters into the ocean, right? You should design it in such a way that this external pressure is not large enough to crush the submarine. Okay. And what if you create a device or create a vehicle that's supposed to go into outer space? Is its design going to be same as that of a submarine? It's going to be the opposite because there, again, inside the pressure is 10 power 5. Outside it's 0. Right? So here there is a tendency for the gas to push the vehicle out, the walls of the vehicle outwards. Right? So here it's going to try and get crushed. Here it's trying to just explode like this. Right? So you need to avoid that also. So if you watch movies where there are space shuttles going in outer space and there's a hole, you might have seen, wind just go into the hole and objects just sticking to it. Because the air is desperately pushing out on the walls. Do you understand? Okay, so it has to be designed properly. So that's the reason I said 20 Pascal is good, because it's very hard for me to just imagine gas at 20 Pascal inside an ordinary cylinder. Okay. Alright. But let us keep it as 20 Pascal. Let's say it is in outer space. Earth is not, the atmosphere is not pushing in all the time. Okay. So dP by dt is given to be 20 Pascal. You have to find the rate of change of volume at this point. You have to find dP by dt. We will write all quantities in SI units. Volume we will write in meter. Notice that the first step is always converting English into. There are some problem solving tips that you should be familiar with. You have to understand that problem solving is a very human thing. What I mean is, we are not computers. There are some aspects that are there that you should be aware of. One thing is, see, there's a point for me writing all this. You can say, alright, all of that was in English. We wrote it in words here and put it all in an order. The thing is, when you look at something that is arranged in a certain order, it's more likely that you will come up with ideas. Right? The first step is to take something that is scattered and all over the place, put it nicely in one organized way, and then stare at it. Right? As you stare at it, you see patterns, you figure out what to do. Alright? If there are things that you can draw, right? So, for example, when I talked about graphs, I talked about the COVID graph and everything, right? It's a very human thing that if you have a bunch of numbers, if you plot a graph, immediately our brain kind of digests it. Right? You know what's happening. Is it increasing? Is it decreasing? So drawing a figure also helps us a lot, which is again a very human thing. Right? So make sure that I'm not doing this as some teaching skill so that you can understand. You are also supposed to do the same thing. Okay? So dV by dt is dV by dt into dP by dt. Right? Now, all these things are known to you. Everything other than dv by dt is known to you. dv by dp we can find out using this equation. Correct? First step is okay. Let's find out what many of you know. Look at this. dv by dp is 3600. Is this correct?
Yeah. Wait, no, it's not.
How should I find that? And for some reason, many of you wrote this. Okay.
No, I don't think that.
Many people. Next.
Not me.
What do we do?
Write V
in terms of P. Correct? Write V in terms of P. So V is 3600 divided by P. Do not put 40, okay? 40 is only at one instant of time. So if you put 40, then it becomes constant. You understand?
Yeah.
Okay. So 3600 by P. So now dV by dt is 3600 is a constant. 1 by P can be written as P power minus 1. Derivative is? Derivative of 1 by P minus P to the power minus 2 minus 1 by P square. Getting it right? P power minus 1 different derivatives. Minus 1 P power minus 2. So you get minus 3600 by P square. These are all capital things. Is this fine? So now we plug that in here. dp by dt is given. So you have to keep this in mind. This is again a common mistake that people make. That value of P that has been given to you, this 40 factor, is at one instant of time. So if you substitute it in the very beginning and then you find the rate of change, you will get 0. Right? Because if you substitute here, the whole thing becomes a constant, but it's not really a constant. Okay? So when you substitute as 40 and you find the volume, you are finding the volume at that instant of time when the pressure is 40. But it's not constant with time. As time changes, both pressure and volume are going to change. Fine. Alright, substitution should be done after you differentiate. Let me give you a simple example where you see that it's obviously not the right thing. Y is equal to x squared. Find dy by dx when x equal to 1. What should you do? First you differentiate. Dy by dx gives you 2x. Then you put x equal to 1. That gives you 2. If I put x equal to 1 in the very beginning, then I get y equal to 1. And if I differentiate, I get 0. You understand? Differentiate first, then substitute. Okay, so now P is given to be 40, 20. What's the answer? 40 squared. 40 squared, yeah. 40 squared. What's the answer? Minus 45, correct? dV by dt is minus 45. Now think about what that minus sign is. Right? So in straight lines, when is the slope negative? Good. When the straight line looks like this. Right? So, and remember, derivative is geometrically speaking slope of the tangent. Right? So if you have a curve that looks like this, can you identify the regions where tangent has negative slope? Till here, tangents have negative slope. From here onwards, tangents have positive slope. And here tangent is horizontal. It has 0 slope. Correct? Now let us interpret the sign of the derivative. So whenever first derivative is positive, that means we have y as a function of x. Whenever first derivative is positive, that is this region, as x increases, y also increases. Wherever the derivative is negative, as x increases, y decreases. Understood? So in terms of physical quantities, the sign of the derivative tells you whether the quantity is increasing or decreasing. Okay. So this tells you as time increases, volume is decreasing. And here as time increases, pressure is increasing. Now we did the math part, but think about it, whether this makes sense intuitively. Right? If I take a syringe, and I close the syringe, block it up with your finger, you close it, and you push on the syringe here, what are you doing to the volume? Decreasing it. You're decreasing the volume. What happens to the pressure as you push in more and more? It becomes harder to push it in. The pressure increases. Right? So isn't this an expected behavior for a gas that when volume decreases, pressure increases? Okay? So it makes sense. I'm saying that it makes sense. You understand? After doing the math thing, alright, let me tell you why we did this. Like we got the answer, right? We could put two lines and call it a day and simplify. Right? Why did I suddenly just start talking about whether this makes sense or not? See, the thing is, after solving the problem, we have to know what we did. Let me tell you a small story about what a student did. Okay. So there was a question. The question was, this was a real question in a problem set that I had given. There is a steel object, I think, a steel object of mass around 100 tons, and it is dropped from a height of 1 meter. Okay. It hits and collides with the ground, and after bouncing off several times, comes to rest. What is the temperature difference of the steel object? This is the question. Now you might find you may not know how to do this. Right? A bunch of data is given to you. Things like you may not have heard about it. There is something called specific heat. There is something called coefficient of resistance. Some fancy stuff is there. All right. But what is the basic question? You drop a steel object of 100 grams from height of 1 meter. It hits the ground. What is the increase in temperature after it hits the ground? One student did all the calculations. He knows all the formula. He knows specific heat, all of that. Did all the calculations and finally got the answer is 100 degrees Celsius. Okay. It should be the answer. It's like 100 degrees Celsius. And I said it's wrong. He said, but where is the mistake? Like, how did you know it's wrong? The thing is, you have dropped steel objects for your entire life. In the kitchen, haven't you dropped some plate might weigh 100 grams. You dropped it from a height of 1 meter. If its temperature is supposed to increase by 100 degrees Celsius, will you be able to touch it after that? No. Right. So remember, this is again something you have to understand. Physics is, I told you several times, but it's very important to understand. It's not something you do on the blackboard. It is not a game you play on the blackboard. It is mapped onto the real world. Right. So after doing this, you should see whether it makes sense. If both of them are possible, you ask yourself, well, something is going on that I don't understand. If this was positive and this was positive, then you're like, what if I compress a gas? Will its pressure decrease? You understand? So this kind of post-analysis after solving has to be done. Okay, for physics problems. Right? It's a way of checking whether your answer is correct or not. Because think about it. Let's say you are an engineer and you got this question. If I drop an object from a height of 1 meter, what is the temperature? What will you do after doing? Will you go to some person, professor, and is this correct? Or will you look at the back of some book? No, this question is not from some textbook. Have you ever thought about this? When you solve a problem, you have answer at the back of the textbook to verify whether it's correct or not. Or you can ask your teacher. But when you are becoming a real life engineer or a scientist, how do you know whether you are right or wrong? Trial and error. So you're designing a bridge. Right? After 100 people die, you're like, oops. I made a mistake. Huh? Yeah. But I'm just saying, think about this. When if you don't have an answer to verify your answer, what do? You need to have stuff, you need to have post-analysis like this being done. There are several tricks. We will teach this to you next year. Right? There are things, there is one thing called looking at special cases. These are all tricks. Special cases, extreme case analysis, special case analysis, dimensional analysis. Right? These are all things that you will learn. And still the thing is, after doing all of this, you will never be 100% sure that your answer is correct. Right? But you can get more and more certainty. As you verify more and more things and it works out, you have more reason to believe that you are right. You understand? This is something, think about this, something really new for you. Because your whole life, You were asked for exact answers, and the moment you gave the answer, someone was there to tell you whether it's correct or wrong. Now think about it. Let's go beyond ourselves. Let's step outside our small lives and think about humanity as a whole. Right? Someone told you F is equal to m. Who came up with this? Newton. But who is he? He's a human being. Right? Isn't it possible that he was wrong? Who are we verifying with? Right? What is the reason you believe in this? You tell me what is the reason you. Physics what? Physics sir. Huh? Physics sir must be wrong, might be wrong. Do you understand? Have you ever asked yourself this? Did you even care whether this is true or false? Or were you just playing a game on the notebook? Yeah, that's right. Okay. So why is this true? How do you know it's true? How do you verify whether it's true? These are all questions you have to understand. And really, this is not true. This is not true. F is not ME. Okay, it's only approximately equal to ME. This has already been discovered 100 years ago that F is not ME. Okay, so why you are studying it is because it works in most of the ordinary life cases. Agreed. So when I say it's wrong, it's not completely useless. It's useful. It works in some cases, and you can use it there. You don't expect it to work everywhere. Right? If someone gives you a pen knife, he gives you a pen knife, okay, and he says, "What can you do with this?" You ask. He says, "You can cut apples and you can cut small fruits and everything." But then yes, can I cut a tree with it? And I say no. Then I don't want it. That's not how it works, right? Okay, to cut a tree, you have axis. That's fine. So Newton was saying that it's always true. We figured out it's not always true. It's true only sometimes. But that's okay. That's good enough. Right? If it's true sometimes, we can use it there. Clear? This is fine. Okay. So because when I was doing this, people were like, "Oh, what?" That's why it's an important thing that you start learning these things right now. Because at the end of first standard, you are going out into the real world. Right? And then you have 4 years of college, and after that, when you go for a work, people will be like, "Just do." That's all. That will be the thing. Okay, they're like, "Just do. Just do this. You clutch plate, you design. I want a car." And you ask, "What am I supposed to do?" I don't know. You just do it. Right? And then you come with some model class. You have to figure out yourself. You are completely lost. This is the story of most Indian engineers. Okay. You study from all HCR, HCR, all answers are there. Right? And finally, when we go to work, something has to be done. And people are completely lost. Right? It's like there are, 100 unknowns and 2 equations. And they say, "How much is solve it?" Right? And you have to find out the data. You have to find out the remaining equations. If you don't have equations, you have to make a best estimate. Right? And this is where we fail. Our education system fails here. Right? Really, this is, you ask anyone who has done engineering and afterwards has worked on something else, they'll tell you. But you do all these problems, they just laugh. Silly things and things like that. Right? But it's important. It is important, but these other things are also important which no one can test you. No exam can test whether you are doing this post analysis. Okay. It's a cone having the radius of base of 8 centimeters and height 40 centimeters. Don't read the question, please. I tell you what the question is. Okay. So there is a cone. The base radius is 8. The height is 40 centimeters. And water is poured at a rate of 20 centimeters per second. Centimeter cube per second. Okay. So water is poured into it. 20 centimeter cube of water is poured into it per second. You have to find the rate at which water level is rising when the water level is 12 centimeters from the vertex. So when the water is at a height of 12 centimeters from the vertex of it, you have to find the rate at which the height is increased.
Wait, what? What is
Is the question making sense? Did you imagine what's going to happen as you pour water into it? Isn't the water level to rise? Correct. Please do all of it yourself. Write in mathematical symbols the thing that is given to you and what you have to find out. So is it daily by daily? Yes. The rate at which falling of the water in the pump is increasing is 20 centimeters per second. Rate at which water is poured into
Supposedly the rate
the formula for volume of a cone is as a cone of radius r and height h. The formula for volume of what you want is dh by dt. Very good. So rate at which height and water level is increasing. We need to find this itself is a part of the problem to understand what really is R. All of this is in English. We have to find dh by dt. So I do the chain rule step. Number of you got it. At least this step, dv by dt, which is given to you, can be written as dv by dh into dh by dt. Okay, correct? This is known. Given this can be found out. And this is what we want. Like most of the problems we solved before, same type of thing. However, there is a small complication in this problem. The complication is volume depends on height and radius. And is radius constant? If you stare at this blue cone, imagine in your mind water level is increasing. Is the radius of the base remaining constant? No. So the volume is depending on two variables. So then you won't have the question. Alright, so that's not enough. Tell me what can be done if volume is 1 by 3 pi h. Derivative of I know what we want is derivative of this with respect to h, right? But we are not then r is also variable and r depends on r. Find r. What do you mean find r? Very good. See, so here is the idea. R also depends on h, correct? As h increases, isn't r also increasing? Right? So it looks like there are two variables, but you can write r in terms of h. And once you do that entire volume, then written in terms of h. Yes, that's what I want. Just pair this figure. R is this. R is this, h is this. Write r in terms of h. You can't give values. Don't give values for this r and h, but you can write r in terms of h. R depends on h. So you should get a relation where you can clearly see that as h increases, r also increases. Right? I'll give you one hint. You are not going to get the answer without drawing the figure, but I'll give you one hint. I'll take the center of this and draw a line joining into the vertex.
So basically, how you find the slant line?
You don't have to tell me. You just draw it in the notebook, stare at it, and then you tell me the final function.
Slant line is the only thing that releases something.
Look at this triangle, the small triangle. Its line is h. Base is r. Okay. Look at the bigger triangle. Its its height is 40. Base is 8. Fine. Now these two triangles are similar. We agree that these two triangles are similar because they are both right triangles and they have common angles. Right? So they are similar triangles. Now can you tell me the ratio that I should write for these similar triangles?
H by
20
40
by 40 is equal to
R by 8.
so R is equal to H by 5. This is what I meant by R in terms of H. R in terms of H. Substitute that here. Now you can do it. Right? So this is the idea. See, look at the general point of this question. When you are given a quantity that appears to be a function of more than one variable, see if those variables are related. Okay. Finally, try to write it as a function of just one variable. Okay. That is the idea. So here that's what we did. We wrote R in terms of H, and finally it depends only on H. Now we can substitute it here. dV by dt is given to be 20. dV by dH, we can differentiate it. We get 5 by 75 into 3 cancels 5 by 25 into h square into dh. Now the value of h is also given. Find dh by dt when h is equal to 9. Substitute h equal to 12. That will give you the answer. Okay. Now what happened to this volume? It's a function of only one variable. Let me summarize. See, we started with a problem where everything was very similar to what we did in the past, except that this thing was troubling us. See, this is just chain rule. We have solved many problems like this. dV by dt can be written as dV by dh and dh by dt. Only problem here was dV by dh. How do we find out when R itself is a variable? That was the problem. Okay. R is a variable, H is a variable, and R and H are related. There are two variables. What do we do? So what we realized is R and H are dependent. We use similar triangles to find their dependence and got R equal to H by 5. Then we plugged it in here, and finally we got V as a function of only one variable. You understand? There is R in the general formula for volume. I'm not saying there isn't any R. Right? But here the R and H are related, so you are able to write it entirely in terms of H. Is that okay? Right? Now you can differentiate. Now you just solve like we solved all the previous problems. Differentiate 5 by 75 into h cube. Derivative of h cube is 3x squared. So that 3 and 3 cancels out. You get 5 by 25 squared into dh by dt. Question is to find dh by dt. Everything else you know. H is given to be 12. You can find out. Correct?
This camera